Welcome to the topic on chromatography. In this topic, we are going to learn in detail about chromatography technique, which is an important identification technique used in chemistry. We will learn about the relative solubility of a substance in a given solvent by calculating the RF value of the substance. RF value comes from the word, the retardation factor. Then, we shall discuss about developing chromatogram using a circular disc of filter paper and make comparison with the chromatogram obtained by linear movement of the solvent. Thereafter, we will move on to learning about locating agents which are often used if the component of a mixture is invisible and how we can use locating agents to make the invisible dots to become visible. We will then learn to interpret the results of a chromatogram, such as finding how many components are found in a given mixture, finding if a substance is a pure dye, which substances make up the mixture, and so on. Before ending the topic, we will learn about some of the important points that we should take note of when using paper chromatography technique. Chromatography is a separation or an identification technique, which is based on the differences in the solubility of a given substance in a given solvent, where each component has a different extent of solubility within the same solvent. An application of paper chromatography is that it can be used to identify the different colored dyes used in a particular ink. Let us look at how to carry out paper chromatography. Take a glass tube and fill it with a suitable solvent. If the ink is water-soluble, then water can be used as the solvent. If it is oil-based ink, then a suitable organic solvent such as ethanol or tetrachloromethane can be used. Use only a small quantity of solvent that is enough to dissolve the ink in the chromatogram. Next, take a strip of filter paper and, using a pencil, draw a line near the bottom of the filter paper. This line is called the baseline, and this is where the sample of the mixture to be analyzed is going to be placed. It is important to use pencil to draw the line. If a pen with an ink is used, the ink in the pen might dissolve in the solvent and interfere with the result. Place a drop of the ink, or the mixture to be analyzed, on the lower end of a filter paper, on top of the baseline that has been drawn. The lower end of the filter paper is then dipped into the solvent. At this stage, we have to be careful that the solvent does not touch the baseline or the specimen under testing. If the specimen is dipped in the solvent, it will dissolve into the solvent directly and will not separate on the filter paper. Once the paper is dipped in the solvent and the glass tube is covered with a stopper or a lid, the solvent will slowly move up the filter paper as the paper gets soaked in the solvent. As the solvent moves up, it pulls the different dyes or the components in the mixture along with it. The more soluble a dye is, the higher it will move up in the chromatogram. In this setup, we can see that blue moved to the highest position and is hence more soluble in the given solvent. Since red moved only a little away from the solvent, it can be considered as the least soluble of all the dyes in the ink. The maximum position reached by the solvent is called the solvent front. Once the solvent stops rising, we can remove the chromatogram paper and mark the position of the solvent front before the paper dries. In that way, we would be able to know the position of the solvent front. From the chromatogram in this example, we can also see that the ink is a mixture of 3 dyes. If there was only one spot, then we can conclude that it is a pure dye. Paper chromatography can also be done using a circular disc of filter paper. We can place the ink and the solvent in the center of the paper and let it spread outwards in concentric circles. Let us compare the chromatogram developed in the linear method with the circular chromatogram. First, place a drop of the ink at the center of the paper. Then, add a drop or two of the solvent above it and observe. As the solvent spreads outwards, the various dyes found in the ink also spreads outwards along with the solvent. As we know, this is the maximum position reached by the solvent and is called the solvent front. The blue dye, which forms the outermost circle, is the most soluble dye, and the red, which is the innermost circle, is the least soluble dye. The relative solubility of each of the dye found in a mixture can be given by what is called the retardation factor, or the RF value of the dye. The RF value is calculated by using the following formula. RF value equals to the distance traveled by the particular component from the baseline divided by the distance traveled by the solvent. Let's say, for example, in this chromatogram, this is the baseline, and this is the solvent front. If the distance traveled by the yellow dye is 6 centimeters, this would become the numerator for the RF value. If the distance traveled by the solvent front is 8 centimeters, this would be the denominator. Therefore, the RF value for the yellow dye would be 6/8, which is, of course, equals to 0.75. Remember to take note that a higher RF value would indicate a greater solubility of the given substance in the solvent, and a lower value would indicate a lower solubility. Another point to remember is that RF value can never be greater than 1, for the obvious reason that a given component couldn't have traveled further than the solvent. Next, let us take a look at what are locating agents and why they are used in paper chromatography. Sometimes, the components of a chromatography may not be visible. In such situations, suitable locating agents can be used to make the components become visible. Ninhydrin is an example of a locating agent which is used with proteins to break them down into amino acids and then color them purple so that the amino acids become visible. UV light is also used as a locating agent to fluoresce many colorless organic molecules. These are some examples of locating agents used with paper chromatography. Let's say we have developed this chromatogram with 4 different specimens. After they are completely dried, we can spray the locating agent onto the chromatogram paper. After a while, we can notice that the spots on the chromatogram begin to appear and become visible so that we can perform our analysis. This is the reason why we use locating agents to locate the positions of invisible dyes in chromatography by making them become visible. What are uses of paper chromatography? Well, paper chromatography can be used to identify the components found in a mixture. Let us say in this chromatography, we use 4 colored pure dyes such as red, yellow, green, and blue in order to test the composition of the dyes in an ink. All the dots are placed on the baseline, and the chromatogram is developed using a suitable solvent to obtain the result shown. What are the dyes that had been used to make the ink? As we can see that the ink is made from mixing red, green, and blue dyes. We can also see that the ink does not contain the yellow dye. Another use of chromatography is that it can be used to check if a substance is pure or is a mixture of substances. In this chromatogram, let us compare a couple of inks. What does the result show? It shows that the ink one is a pure dye since it contains only 1 dot. However, we can see that the ink 2 is a mixture of 3 different dyes, since we can see 3 distinct dots for the ink 2. Another useful information we can get from chromatography is that we can identify the exact number of components found in a mixture. For instance, in this chromatogram, we can see that the ink one contains only 2 dyes, but the ink 2 contains 3 dyes as shown by the respective number of dots for each of the inks. Another information that can be derived from chromatography is to be able to determine which is the most soluble and which one is the least soluble substance found in a mixture. In this chromatogram, we can see that the blue is the most soluble component, while the red is the least soluble component. The green dye is somewhere between the two of them. Another use of paper chromatography is to be able to determine the relative solubility of the components of a mixture by finding the RF values for each of the components. For instance, in this chromatogram, the RF value for the red dye would be the distance of the red dye from the baseline, which is 2 units, which is then divided by the distance of the solvent front from the baseline, which in this case is 10 units. This gives an RF value of 0.2 for the red dye. How about the RF value for the green dye? Let's say the distance for the green dye is 4 units, and its RF value would be 4 out of 10, which is equal to 0.4. If blue dye is 8 units away from the baseline, then its RF value would be 8 out of 10, giving a 0.8. Thus, by knowing the RF values for each of the dyes, we can determine the relative solubility of the dye in the given solvent. The next use of chromatography is that it can be used to identify the amino acids found in urine or blood samples of patients. In this analysis of the urine specimen, we can see that the urine of the patient contains alanine, histidine, and serine. Apart from the above uses, we can also use chromatography to identify the ions present in a mixture or find out the different type of dyes used in food colorings. There are many such applications where chromatography can be used. Let us take a look at one example of interpreting the chromatogram. The chromatogram can be interpreted by using known dyes or substances for reference. On the starting line, 4 pure dyes are placed, along with 4 inks, 1 to 4 for analysis. What are the deductions that we can make from this chromatogram? Firstly, we can see that ink 1 is a mixture and it is made of red, green, and blue dyes. Next, we can see that ink 2 is made by using green and blue dyes only. Likewise, we can see that ink 3 is made of yellow and blue dyes. Ink 4 shows that it is a pure dye made of green dye only. Another one of the interpretation we can make is that blue is the most soluble dye of all the dyes, while the red dye seems to be the least soluble in the solvent. Before we conclude this topic, let us look at some important points to take note. For paper chromatography to work, it is important for all the components to be soluble in the same solvent. Otherwise, we would not be able to get accurate results. Paper chromatography is only an identification technique, and it cannot be used for large-scale separation of a mixture into its components. Paper chromatography cannot be used to determine the quantity of each of the components in a given mixture. Rather, it can only be used to identify them qualitatively. The starting line should only be drawn using pencil or graphite. Inks cannot be used since the dyes in the ink may also separate, and this would interfere with the results. The starting line should be clearly above the solvent in order to prevent the dyes from dissolving directly into the solvent. In such a case, the dyes would not appear on the chromatogram correctly. Longer chromatogram gives a better resolution of the separated dyes, which would be further apart from each other. This would make it easier to identify the components or enable us to calculate the RF values much more accurately. That's the end of this lesson. Hope you have enjoyed learning this topic. Till we meet again, have a great day from all of us at Donison Dean Research Center, Singapore.